do problem 2266, count number of texts. Since we're talking about text, why don't you write some text in the comments about a problem you would like to see solved. I'm open to pretty much anything. Right now I'm emphasizing dynamic programming kind of questions because that's probably my weakest, probably the weakest category for me personally, right? I have the most trouble with those kind of problems, so I think that I should kind of reinforce those ideas going forward if I want to get better at data structures, algorithms, Leetcode contests, whatever. But that doesn't really matter for the nature of this problem. Let's just go ahead and get right into it. So Alice is texting Bob using her phone. Good for you, Alice and Bob. I'm glad you guys are communicating. The mapping of the digits to letter is shown in the figure below. Okay, so this is throwback, right? Early 2000s texting using, this 10-digit scheme or whatever. In order to add a letter, Alice has to press the key of the corresponding digits I times, where I is the position of the letter in the key. So if Alice wants to type the letter S, then she has to press 7 4 times. Why? Because 7 is here, right? If you press it once, you'll get P. If you press it twice, you'll get Q. If you press it 3 times, you'll get R. And if you press it 4 times, you will get S. Note that 0 and 1 do not map to any letters, so Alice just doesn't use them. I think 0 is a space. Yeah, that's a space, and I don't remember what 1 does. But back in the Dizay, I'm not that old, so there was a very small period of time where we would use these, but I remember my older brothers would. Who cares? However, due to some error in transmission, Bob does not receive Alice's text message, but instead receives a string of pressed characters. For example, when Alice sends the message Bob received the string 2266622. Right, and why does that happen? Well, if you have 22, that's mapping to B, right? Because she clicked 2 twice to get B. She clicked 6, 1, 2. She clicked it 3 times to get O, and then she clicked 2, 1, 2 twice again to get B. So bang, bang, B, bang, 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 O, bang, bang, B, Bob. Okay? Given a string, press key representing the string received by Bob, return the total number of possible text messages Alice could have sent. And then since this can grow quite rapidly fast, right, we want to mod it by 10 to the 9 plus 7. All right. So the issue is what? Well, if I asked you, I want to type the letter M. I want to type this sequence, and I also just want to type 1N. What would that mean? Where you're like, okay, I want to type MM. So that means I'm going to do, I'm going to hit 6 once, wait, and then I'm going to hit 6 again. Okay? What if I want to type N? Well, if I want to type N, I'm going to hit 6 twice. Okay, well, if Bob is receiving this message, he's going to see 6. So he doesn't know, did you type MM or did you type N? Right? There's a collision. This can be 2 different things. Just because I received 6, I don't know if you typed MM or if you typed N. So that gives me 2 options for what this could be. Right? So that's why there can be multiple solutions. So if I'm given 2, 2, 2, 3, 3, well, for 2, what can 2 be? 2 could be just an A. Or this could be B, right? It could be these first 2. It could be B and then A. Or it could be just a C. Or it could be A for the first one and then B for these next 2, right? And I'm just talking about this section, right? And then you have to multiply in what can be over here, right? Well, for 3, 3, this could be 2 Ds or it could be an E. And these can go to any such solution, right? Because I kind of split these things up. So that means that there's 8 different combinations of things that this could be. And you can enumerate through all of them, and I'm pretty sure that this example does that, right? There's 8. And if you look at an example like this, where it's just, not a ton, but there's, someone kind of rage pressed 2, you get, what is that, a billion? 2 billion possible combinations. So this blows up really fast, which is why we're probably modulating it, right? But you can see that just because you receive these press keys, there can be multiple things that end up resulting in this message. Now, this is a strange thing to... Oh, I see what she was sending. Alice sent Bay. They're dating. Alice and Bob are together, dude. Juicy. Okay, so let's go ahead and get right into this problem. Okay, so let's kind of walk through this system here and think about each of these characters. And now I'm going to draw each of these characters as individual nodes. And I hope that makes sense later. For now, just think of it as a weird, strange way of writing down these numbers. Now, when I see a 2, right? When I see a series of 2s, what is the possible thing it could be? Well, if the first letter I type is A, that would mean that I'm at this node here, right? And if the first letter I write is B, that means I'm at this node here. And if the first letter I write is C, it means I'm at this node here, right? Meaning that I typed 3 2s in succession to get to C, or I typed 2 2s in succession to get B, or I typed 1 in succession to get A, right? All right, so that means what? What does it mean? So there was what? There was So if this was C, sorry, I'm just thinking about how I'm going to explain this. If this was C here, let's get rid of this idea. I mean, that makes sense, right? So what possible things could get me to just typing 1 2? Let's say that. Let's start there. Well, just typing 1 2, I either the only thing I could have done is placed an A. That's the only thing that could be there, right? What if I have 2 2s? What could be the case? Well, I could have typed 1B, or I could have typed 2 A's in a row, right? What about when I get to this case here? Well, I could have typed a C. I could have typed a B and then an A. Or I could have typed an A and then a B. Or I could have typed, or to get here, a C, a B, A, and then an A, right? An A, B, and then an A. Or a B, shit. Not 2 A's. Yo, what am I doing? In order to get to this final C, I either typed what? I typed just a C, right? Because a C is 3 2s. Or I typed a B and then an A. Or I typed an A and then a B. Is that right? Or I typed a 3 A's in a row. Okay, so those are the 4 possible things I could have typed to get here, right? To get to this point where there's 3 C's. Well, what does that really mean for A? If I type just a C here, that means for C, I skipped all of these options here. Does that make sense? Because since I'm typing a C, I typed 3 times to get to C. If I typed a B and then an A, if I typed an A, what does that mean? That means that I went from, we'll go backwards, actually. Sorry, I'm all over the place, but I think I'm starting to get a way of explaining this. If I typed a B, that means I had to type 2 B's in a row. So I went from here to here. Does that make sense? Because I typed a B, so I had to use these 2 2s to type a B. If I typed a C, I had to use these 3 2s to type a C. So I'm using these arrows to just kind of represent what I had to skip in order to get to this system. Okay? And if I typed an A here, that means I must have used just the last system here to get there, right? Because I only had to use one such node to get to this place here. Now, what can I type at this 3? Well, there's only one 3. So the only way I could get 1 3 is if I typed a what? A D, right? So there's a D here. And I only use one thing to get to a D, so I just used the last system here. Now that I'm at 2 3s in a row, I have options, right? I could either have had typed a D or an E to get to 3. If I typed a D, then I use the previous system. If I typed an E, I use 2 away to get here. So in kind of summary, let's go through this again and make it make a little bit more sense, because I kind of realized as I did it how I should explain this. So there's a nothing here where you started. So if I'm at this point, what could I have typed? Well, it's only 1 2. So the only thing I could have typed here with 1 2 is an A, right? What about when there's 2 2s? There's 2 2s in a row. So I could have either have typed an A or I could have typed a B. What about when there's 3 2s? Oh, well, there's 3 2s. It could have been an A here. It could be a B here, or it could be a C here. So when it's just an A, all I have is this situation here. When it's just an A here, all I have is that A there. When it's just an A here, all I have is A there. In order for this to be a B, right, I didn't type that first A. I used the first 2 things to type the B. Same with here. If I didn't type that there, I'd use these first 2 things for this to be a B. And then in order for this to be a C, I used the first 3 sequences to create the C. So I didn't type that there to make this a C. For some reason, this went away. In order for this to be a D here, it can only be a D, right? It can't be an E or an F because it's just 1 3 in a row. I typed the 2 and then got there. For this could be either a D or an E. If it's a D, then it's just this link here. If it's an E, then I skipped that first 3 because I had to use the first 2 to make that an E. And then again, we should probably have some sort of recognition with the idea of these things, having. So what do I do with this directed acyclic graph now? Which all dynamic programming, so this is kind of revealed the nature of this problem unintentionally. But for a dynamic programming, for a system like this, well, the number of solutions is the sum of the solutions for what can be in a place. Meaning the solution for this node here, well, there's only one thing going into it. So the only thing that could possibly be here is A. Right? That's the only thing that could possibly be at this slot here. When we get to this slot, why are my colors all over the place? When we get to this spot here, well, it could have led from here, or it could have just led from itself. So if it led from the first thing, right, if it was this link here, it's AB. But if it led from this link here, it's B. Right? If we get to this final spot here, well, if it led from this node, then it could be AB. Could be ABA. Right? Wait. Sorry, not ABA. Sorry. This is AA, right? Because the A is this link, this blue link. I'm all over the place. If we get here from there, then this is A. If we get from the first node here using the red link, that's the AB case. And then if we use this final length, that's the C case, right? And this has two solutions actually. So when this link passes through, it could be AAA or BA. So all of that is to say, the number of solutions you add on to that number of solutions. So this thing here, right? It has two solutions. It has A and B. So when that information gets propagated, right? When that information gets propagated down this link using the A, this is the A length, you can attach A to both of those solutions, right? So then you could have AAA or BA, right? And that's from here. So the number of solutions for a node, right? For a general node, X, the solutions, I'll call it D of X, is, well, the incoming edges of X, right? So if there's these nodes going into X, U1, U2, U3, they all have edges into X. It's the sum of UI. It's going to be U1 plus U2 plus U3, right? The number of solutions at this node is the number of solutions just using this node, which is C, right? So if this was 1, plus the number of solutions at this node. And how many solutions did this node have? Well, it was either AA or B, so 2, plus the number of solutions down this link at this node. And how many solutions are at this node? 1. So there's 4 possible things that could be at this node. And you have to keep playing that game down this tree, down this this graph. So how do I know if a system has how do I know the links going into a node X, right? So if there's all these previous links, how do I know if there's a an edge? Like, notice in this problem, the way that we had it, let's go back and let's clean this up just a little bit. The way we had it is like, there's edges sometimes going into things and sometimes there isn't, depending on like the context, right? Like when we look at, notice there's no edge going from this to this 3, right? The number of edges going into something is the number of times in a row that you've seen that thing, right? Because like, let's just do another example. If we see DE, that would mean that the user typed, oh, that's a bad example. Let's say DG. If it was DG, that would be 3. And then for G, that would be 4. Right, so obviously you would know what this text is because both the characters are unique, so you could easily identify, okay, there's only one thing this could be, right? So when it was 3, 4, well, the only way you could get here is by typing 1D, and the only way you could get here is by typing 1G. But if you had a message with, say, 4, 4, okay, so if you were given this screen text here, again, this could be multiple things because it could be GG, good game, or it could be just an H. So how does that work? Well, if you're given these two characters, if there's 2 things in a row, then you're going to have the choice of doing one thing twice or using it both. But if you have a system where it's 3, 4, like the DG example, right? There is no skipping because there's only one option for what you could do. So there's no skipping nodes. So basically, you can consider the k previous if what? You can consider the k previous nodes always, right? Like for this, the sequence is 3, right? 2 occurred 3 times, so we can consider the last itself and the last 2, which is 3. So the 3 previous nodes. Right, really the 2 previous nodes, including yourself. Right, for this system where we get to this point where it's 2 and 2, 2 occurred twice in a row. So you can consider the last 2 nodes. And how does that limit? What if you had, let's say you were given the text 2, 2, 2, 2. How would you manage this situation? Well, you have it such that, right, that, well, they could have just typed an A, right? Or they could have typed a B, or from here they could type an A. This can go here, or here, or here. Did I miss any? Notice there's 1, 2 in a row, so we have one link. One edge going into it. There's 2 2s in a row, so there's 2 edges going into the system. There's 3 2s in a row, so there's 1, 2, 3 edges going into the system. Now, what about this 4th 2? Should I then have 4 edges going into this system? Should I consider the last last 4 things? Well, the only caveat with this problem, right, where that no longer becomes true is that, well, you don't need to consider, it can only be A, B, C. Right, when you type a 4th thing, if you type the same letter, if you type 2, 2, 2, it has to be one of these following things, right? Because there is no 4 option. You can't hit 2 4 times and get something new, right? It's constrained by these 3 things. It's either A, B, or C, right? There's no way that I can, because like the idea was when I created this link and I skipped over the 2, it's because I was typing a C, right? When I created this link to skip over the first 2, it's because I was typing a B. And when I just went here and didn't skip over, that means I was typing an A. Lowercase a, I guess. But what would it mean if I skipped over here? Well, that means I was not typing an A, I wasn't typing a B, I wasn't typing a C, I wasn't typing anything. It doesn't make any sense. I can't skip that many because there's only 3 options for 2. Right? The number I can skip is constrained by what I can actually type. Now, what could have happened here, though, right, is it's still the same situation where maybe I typed a B here, and then I skipped 2 to type another B, right? So I can still, if there's the maximum backwards I can look at is 3 for this, for 2. Now for 7 and 9, they're unique because 7 and 9, it could be 4 things. So I can't hit the letter 4 times to get to S. I can't hit 9 4 times to get to Z. Okay. So with that, let's try to do this problem. I think I've explained as much as I can. I guess one final caveat, since you can't go farther back than 4, we only need to keep hold of the last 4 previous nodes. Right? Because what we're going to do is we're going to kind of look through these nodes one at a time, but we never go farther back than, oh my God, you guys probably think I do coke or something, huh? That's just a weird twitch, okay? I don't do drugs. I do diet coke. So we don't need to actually go further back than just checking the last 4 things, because you can never have an edge that's longer than size 4. right? Because if there was P, Q, R, S, T, or whatever, P, Q, R, S, T, right? I can never have an edge that looks like this. And these edges, sums get updated by the previous thing's sums. So as long as I keep the last 4 pieces of information, I never need to update. And that'll give us a constant time, constant space algorithm. So how does this work? Well, we got to keep the count of the character that we've seen. We'll assume the count first is -1, I guess, and the character we've seen first, we'll call it 0. It doesn't matter. All right. And then what are the last things you can, well, for everything but 7 or 9. Yeah, we'll not worry about that right now. Let's say, so remember, we have to look at least the last 4 things, right? So we'll say last 4 is 1, 1, 1, 1. So that'll be what we set the beginning of our dynamic programming array to. And we'll look at each key and press keys. And we'll update the count, right? Because we want to have a running sum for how many times we've seen something in a row. Because how many times you've seen a character in the row determine how far you can look back, right? The number of times I see 2 in a row determines how many previous things I'm going to add to 2. So if I've seen 2 twice in a row, I can look at the 2 previous things, right? If I've seen 2 3 times in a row, I can look at the 3 previous things. So keep a count of how many times you've seen previous things. So count and char. Well, count's going to equal itself times char equals key. So char is the character that you're looking at right now. If it equals the key, then you'll hold on to your previous count, but you always have at least a count of 1, and then char will be equal to key for the next time you run this. Now, your count can't get greater than what? Well, it can't get greater than 3, because after you see something 3 times in a row, like for DEF, all right, let's say for the number 2, right? The largest count you can have is 3, because that's the last 3 things you can consider. Because if you type 2, 2, 2, 2, right, only 3 of those things at max would map to a unique number. After that, you're typing a new sequence of numbers, right? That's the example that we determined here. Right, if you type 2, 2, 2, 2, you don't get an additional edge like this. Okay. So the max is that, and 3 plus, if the character equals 7, then you get an additional 1, or the character equals 9. Right? So if the character equals 7 or 9, then you get an additional look back, right? Because for 7 or 9, you can look back for 4. So for every single one, you get 3 things, 3 past nodes you can look at, except for 7 and 9. So if there's 7 or 9, you get 4. So this will just give you an extra 1. Okay, and then what does that mean? Well, you would then just add up. Your last 4 would then be, well, you would update your last 4. So if these were the last 4 nodes you were looking at, your new first node is the sum of the count that you can look at, right? Because the value... Okay, this is not opening anymore for some reason. Oh, because this is in the way. The value of 2 for 3 is the sum of these previous 2. I'm just like continuing to do, right? The value of hard work is the belief that your work has value. It's called a circular argument. Right? Remember, we've determined that the value for this 2 is the sum of all 3. Right? So if this was the last 4, even though there's just 3 here, the value of this is the sum of all these last 4. But then after this is done, the last 4 is then this. And after this one's done, the last 4 becomes this. So we have like this moving box, right? So if like you have these nodes, your last 4 would be this. And then when that operation is done, you'd pop this one from the stack and then insert this one into it. So that would give you this as being your last 4. So I'll sum up the count and I'll put that into the array. The last 4 things in the array. But only the account amount, because that's the number of the paths that I can add up together. And then I'll add up the last 4, excluding the last one. Because I don't want to add in the last one, because the last one is garbage. Right? And I think that's what this will do. So I'll disregard the oldest one, and I'll add in the newest one. And then when I'm done, I'll just return last 4. And then we get a syntax error. Perhaps you meant equal equal. I did mean equal equal. This is saying 40, so I already know this isn't good. Okay, not the max, the min, right? Because it can't get greater than this. You don't want to set it to the max, because then it's always going to be... No. Okay, so this is saying 8422 for the sequence 22233. Maybe it'll be beneficial. All right, we're going to return the last 4 at 0. But let's print the last 4 after each iteration. So after the first iteration of last 4, so for 2223, all right, let's just quickly do this. The last 4, well, this is just 1. This can occur once. But then when you get here, there's 2 things that could happen, right? Because you could go from here or you could skip here. So when you have these as the last 4, you get twice in the top. And then when you get to this third one, the third 2 can happen 4 times. There's 4 different ways that could happen. And then it's trailing. Notice how it's moving like this, because everything's getting shifted to the, getting shifted over every iteration to always keep hold of the last 4 things you've seen. Now this might be a little bit more complicated, but now the space complexity is constrained to just 4. So we don't have to, So we don't have to worry about the fact that, you know, it doesn't blow up with n. And just having 4, that's constant, right? So let's go ahead and submit this. It's going to give me an output error because I forgot to do this. And I also forgot to do what I always forget to do, which is mod this by 10 to the 9 plus 7. Why is it so slow? This should be really fast. All right. Probably get a better runtime because a little modular arithmetic, you don't need to, you can mod a mod, it's the same thing. So maybe it'll help us keep things from scaling too fast. All right, there you go. So hopefully that makes a little bit of sense. The edges are just the things that we're going to sum together in our final solution. And then at the end, whatever the values for the last thing is what's going to be the answer. We can actually make this a little bit more shorter. A little shorter. A little bit more shorter. A little shorter. Just so we can have a really cool short solution, which is efficient. And so basically, the number of things we can look back is the number of times we see something in a row to a limit, right? Because we can't, looking at something 10 times in a row doesn't mean there's a key that corresponds to typing the same key 10 times, right? There's not a letter that corresponds to typing the same key 10 times. So it's either you can type the same letter a maximum of 3 times to get a unique character, or 4 times if it's 7 or 9. You keep track of the last 4 things you see because At maximum, you can only sum up the last 4 things. And then use this little tricky approach so you can always keep hold of just the last 4 things as you kind of slide down the numbers that you've seen. And yeah, that's the solution. So the runtime, right, you just have to look at each key, and it's a one-time pass. So that's O of n, right, because we just look at each key once. And this is a constant time operation. This is a constant time operation, right? There's kind of, we have to keep rebuilding this last 4 thing, but we're only keeping hold of 4 things, so that's constant. And then for space, well, we just have 4 things we need to save and then a few variables, but it's not dependent on n or anything. So for time, we have O of n, and for space, we have constant. And yep, hopefully that makes a little bit of sense what I did here. I think the idea is maybe you should always try to model your problem as a DAG if it's dynamic programming, because dynamic programming problems can always be modeled as a DAG. And this is a DAG system, and the edges depend on the count of the thing you've seen, right? And then you can just sum up those previous edges and build your dynamic programming array like that. All right, please like and subscribe. And tell your friends about my videos. Maybe you like them. I know my graph videos are much better than my dynamic programming videos, but I'm still learning how to do dynamic programming properly. So thank you guys. Have a good day.